Welcome to Evidence Mastery with Dr. Massoud Toussi. Whether you're a professional in pharma, healthcare, academia, a regulator, an HTA body, or a student, understanding exactly how to transform raw, messy, operational healthcare data into credible scientific evidence is absolutely vital. So today's explainer is going to focus right on that process as we dive into the chapter titled Data Quality and Fitness for Purpose.
Okay, let's just bust a huge myth right out of the gate here. A lot of people think data quality is this absolute binary state, like data is just universally good or universally bad. But actually, data quality is completely relative. A data set that works perfectly fine for describing general prescribing trends could be completely useless if you're trying to figure out the causal effect of a new drug on some super rare adverse event. You know? It's all about context.
So let's dive right into this. Our roadmap for today covers 5 key areas: quality dimensions, missing data mechanisms, modern dashboards and scoring, regulatory fitness for purpose, and finally, cleaning and mitigation strategies.
All right, Section 1, Quality Dimensions.
To systematically evaluate real-world data, the research community relies heavily on 4 core dimensions. These basically give us a structured, standardized vocabulary so we can actually talk about data limitations. So, here's our foundational definition. Data quality is the degree to which a dataset is suitable for its intended use, and we evaluate that across completeness, accuracy, consistency, and timeliness. Oh, and a golden rule to remember here. In real-world data, missing information is the rule, not the exception.
Let's zoom in on completeness for a second. This can trip you up at the patient level, the variable level, or even the event level. Take oncology registries, for example. When really critical variables like tumor grades or specific biomarker statuses, think HER2 and breast cancer, are just missing, it severely handicaps your ability to run granular survival analyses. And worse, it can introduce some pretty nasty systematic bias.
And the sheer scale of this missingness is honestly kind of staggering. A recent study looking at the highly regarded SEER and NCDB databases found that 13 to 29% of patients were missing at least one key tumor variable. Crucially, this missingness was independently associated with worse overall survival. That means the patients with incomplete records were systematically different from the folks with complete ones.
Then we've got accuracy and consistency. Remember, real-world data is usually optimized for billing, right? Not for scientific precision. For instance, an algorithm designed to identify a myocardial infarction might look highly accurate if you just check billing codes. But that accuracy plummets if you don't have the corroborating lab or ECG data to back it up. Consistency checks are a literal lifesaver here to catch crazy logical contradictions, like a male pregnancy diagnosis, which any basic algorithm can spot as totally impossible.
Moving right along, Section 2, Missing Data Mechanisms.
So missing data isn't just some vague incompleteness that you can brush off. It's a distinct methodological challenge, and it requires totally different handling depending on the underlying mechanism causing it. The first one is missing completely at random, or MCAR. This is when the probability of a value missing is completely independent of any data whatsoever. Think of it like a transient software glitch that just randomly fails to save a cholesterol value for 2% of patients. It's definitely the most benign form, but unfortunately, true MCAR is exceedingly rare in real clinical data.
Next up is missing at random, or MAR. Here, the probability of missingness depends only on observed data. So, for example, let's say body mass index is a lot more likely to be missing for your elderly patients. If age is reliably recorded in your dataset, then the missingness is at random, conditional on age. And because it's tied to an observed variable we already have, we can actually address it mathematically.
And finally, we have missing not at random, or MNAR. Now listen closely, because this one is highly dangerous. This happens when the missingness depends on the unobserved missing value itself. Imagine you're running a mental health study, and patients with really severe debilitating depression are just way less likely to fill out a symptom survey. The missingness is driven by the severe depression itself, which is exactly what's missing from your data. That introduces a massive unmeasurable bias.
So how do we treat these? Well, MAR is manageable. It lets us use advanced statistical techniques like multiple imputation, where we essentially predict and fill in the blanks using the observed variables we do have. But try that on MNAR, and standard imputation will completely fail. Because MNAR is driven by hidden biases, you really have no choice but to rely on complex sensitivity analysis.
Okay, Section 3, Modern Dashboards and Scoring.
Historically, checking for all these data issues meant writing out these manual, highly error-prone SQL queries. But today, we rely on systematic data quality assessment matrices. Tools like the OHDSI data quality dashboard are incredible for this. They run over 3,000 distinct automated checks across those dimensions we just talked about. It takes mountains of raw data and instantly aggregates it into a clear pass, fail, or warning status based on acceptable thresholds. It gives researchers this amazing high-level view of data reliability instantly.
Which brings us to Section 4, Regulatory Fitness for Purpose.
Look, all those fancy dashboard scores don't mean a thing if we can't connect them to our ultimate goal, proving the data actually works for regulators. And this brings us to the fitness for purpose paradigm. The goal isn't to walk in with a perfect 100% data score across the board. The goal is to prove, without a doubt, that the data set is an adequate, reliable tool to answer your specific research question or support your regulatory decision.
And fitness for purpose has truly become a synchronized global standard. The FDA really established this back in their 2018 framework, putting a huge focus on the context of use. The EMA followed suit, completely embedding it into their Darwin EU network in 2022. And now the forthcoming ICH M14 guideline is poised to make this kind of prospective data quality assessment the absolute global gold standard for real-world evidence.
Want a landmark example of this in action? Let's look at the FDA's 2019 approval of palbociclib for male breast cancer. Now, male breast cancer makes up less than 1% of all breast cancer diagnoses. Running a traditional randomized controlled trial for that is virtually impossible. But by utilizing real-world data from multiple databases and applying really explicit quality criteria, the sponsor proved the data was fit for purpose. They provided sufficient evidence for a label expansion despite the incredibly small sample size. It was a real game changer.
All right, the home stretch. Section 5, Cleaning and Mitigation Strategies. So, identifying errors is really only half the battle. Now we have to actively mitigate them so they don't lead us to biased conclusions. Rule-based cleaning actions applied right during the data extraction phase are your crucial first line of defense. These deterministic rules automatically flag or fix obvious errors, stuff like biologically implausible blood pressure readings, ensuring a diagnosis date actually precedes a treatment date, or standardizing different units of measurement across various databases.
Now, whatever you do, you can't just go deleting incomplete records. Doing that causes severe selection bias. Instead, statistical multiple imputation has pretty much become standard practice in huge networks like PCORNet. Also, when you're mapping local codes to standardized terminologies, which we call algorithmic harmonization, you cannot just blindly assume the algorithm is right. It requires rigorous validation sub-studies against a true gold standard, like manual chart reviews to be sure.
Which leaves me with this final challenge for your own research. When data issues can't be perfectly resolved, and let's be real, they rarely are, radical transparency is your absolute best mitigation strategy. Always question the underlying missingness. Try using sensitivity analyses, like a tipping point analysis, to systematically push and pull on your assumptions. You want to make sure your primary findings are truly robust before you go making any major scientific claims.
And that brings this explainer to a close. The insights, the examples, and the strategies we discussed today are actually taken directly from my upcoming book, Real-World Evidence, Sources and Solutions, which will officially become available this year. So before you boot up your software for your next analysis, ask yourself, is your data just good, or is it genuinely fit to answer the exact question you're asking? If you found this breakdown valuable, I'd love to invite you to subscribe to the Evidence Mastery channel to see many more videos about real-world evidence and real-world data. Thank you so much for joining me, and keep mastering your evidence.